Well, the moment has arrived. The final board of this chapter, and hence the proof of probably the most famous result in all of theory of computation. Proof that effectively some things just cannot be done in broad interpretation. More specifically, we will show the existence of a language that is not only not decidable. We will go further, we'll go a step further and show that it's not even Turing recognizable. In other words, there's no Turing machine that will accept on all strings of the language. Can't even do that. So this board, these 4 sessions will be effectively showing these 2 things. So two theorems. One, 2, and a corollary. In fact, it's the corollary which is the punchline. And I've promised you that when the moment arrives, I'll give you a fanfare. So it won't be until the end of the 4th session. The previous day, my flu was pretty bad. I don't know if you notice much of a difference after one day compared to yesterday's symptomatology. I still feel pretty miserable. That's what flu does. But I'm still hacking up green phlegm, so my body's still fighting furiously the virus. But it's not as voluminous as a day ago, so I hope that means I'm on the mend. At least I'm not at the trough, but starting to climb up again. Anyway, so we'll start with showing the existence of a language. But we already know it's going to be ATM. We'll show that that language is not decidable, and then we'll go on and find a related language connected to this one, closely connected to this one, which is not even Turing recognizable, right? Which is sort of far worse. So there are some languages for which even the Turing machine is just impotent. Not only is it unable to decide the language, can't even recognize the language, right? And that's significant. That's powerful. When it sinks in, like in fact, Turing was, I've said this earlier, but Turing was actually not the first to prove mathematically that certain tasks just had no solution. That honour went to Church, the American mathematical logician. Not that Turing is not, but well, he's not American, but did his PhD in America at Princeton. Met Gödel, because Institute for Advanced Studies, where Einstein and Gödel were at, it's very close to Princeton, and von Neumann, Johnny von Neumann, was strongly impressed by Turing, and even invited him to become von Neumann's assistant. And Turing refused. He didn't like the way the Americans threw money at problems rather than, I'm paraphrasing him somewhat, but he didn't like the way Americans threw money at problems rather than throwing thought. So he's somewhat cynical. So he went back to Cambridge. Right, but Turing's result, the famous halting problem, can you just... Well, usually it's formulated slightly differently because it sort of sips its thing. It puts everything in terms of languages. But normally the halting problem is described, is there a Turing machine that can decide when the input is it's almost the same. When the input to that Turing machine is a description of another Turing machine, or of a Turing machine, and a tape that goes into that Turing machine, can that first Turing machine decide, yes or no, whether the Turing machine, the model of the Turing machine goes in, the description of it, that goes into, it's confusing, we're talking about two different Turing machines. I'm just wondering how to label them. So there's two different Turing machines. All right, I'll talk about the Turing machine real, right? Turing machine real, and the other one modelled. So the Turing machine modelled. Okay. So the question is, is there a Turing machine real that can take as input a description of a Turing machine modelled and a tape that goes into the Turing machine modelled, okay? And then that Turing machine real, can it decide, yes or no, whether that Turing machine modelled and the tape that goes into it, will that Turing machine modelled halt or not halt? Can the Turing machine real make that decision that it will halt or it won't halt? Can it make a decision? That's the halting problem, okay? As it's usually formulated, but SIPSA sort of translates it somewhat into a sort of language type problem. So misses the historical impact. That's why it's called the halting problem. Can you find a Turing machine real that makes a decision, yes or no, whether this Turing machine modelled and its tape, whatever tape it is, will the Turing machine modelled halt or not halt? And there's no such machine. There is no such real Turing machine real. It doesn't exist. And Turing proved that it cannot exist via his use of the universal Turing machine, UTM. So Sips is a bit idiosyncratic the way he does things. So he barely, like a line or two, barely mentions the universal Turing machine, the UTM, which features heavily in most other texts. So I will give. I mentioned it earlier. I don't have it with me right now, but I'll give a course definitely on Marvin Minsky's book, Finite and Infinite Machines, and he has a whole chapter on the Turing machine. So what you're going to get on this board, very SIPSA-ish, is it's equivalent, obviously, but it's not the sort of standard way most texts handle the famous halting problem. But it's equivalent, and it's pretty nice. The dramatic impact's there, and if you let it sink in, the full impact of what it implies, the philosophical implications are enormous. It means, provably, that there are some tasks that will just never be solved. Right? No matter how much scientific progress, concept, improvement or whatever, it's just never going to be solved. Provably never will be solved. Right? I mean, think about it. It's stunning, and we're going to do it today. Right. So, pity I'm a bit under the weather with the flu. Could have made the presentation a bit more dramatic, but I hope you'll be pleased with the trumpet roll at the end. That'll be promising. Okay. So first part we're going to show, as saying a bit earlier, we will show that there is a language. We will show that this language is not Turing recognizable. Now that's not as dramatic as showing the existence of a language, so effectively a task, the existence of a language that is not even Turing recognizable. That's far more damaging, far more significant. That means that the Turing machine can't do anything. It can either, it not only can't decide, it can't even recognize, which is even more impotent. Alright, so now, now this little bit here is repeated from the bottom